Okay. So 2 weeks left, guys, and then the final. So information this week and information next week will be the last of it for Chem 102. And then you'll take the final exam. If you guys would like to pick up your midterm to see, I know that I put the scores on, but if you want to see how you did, I can drop those off at the campus. And you can pick them up in the library. Otherwise, I mean, the scores were really well, I thought. You guys did well. So if you don't live in Tahoe, let me know and we can arrange, another way to get it. But just keep me posted on that if you want. Next week, next Tuesday, your research abstract is due, your final draft. So you got 1 week from today. And then on Thursday of next week, we're going to do presentations, 5 to 10 minute presentation. You just pull up your poster. You're in the PowerPoint slide from the template that I posted in the research page on Canvas. Just pull that up and share your screen. Or if you feel like you have technical challenges, you can email me that presentation potentially, or submit it to Canvas, several ways, and I can pull it up. But essentially, you're going to present from that poster that you create, okay? And so that is coming up, right? Next week. So please be working on that. If you guys have any questions, shoot me a message, see me during office hours. There's usually time in lab to discuss those things too. So we just want to make sure I want to make sure you're in the home stretch in a good, comfortable position. So with that said, yeah.
Sorry, is Erina just going to email us back about the rough abstracts? I just haven't heard anything. I turned mine in a little bit late, so.
Okay. I was about to ask the same thing.
Let me ping her and see where she's at with those rough drafts, and then I'll let you guys know. Hopefully, yes, it'll be sooner than later because I want you guys to be able to see what her feedback is. Now, that's an ideal situation. If you don't get it back from her, then just stay the course. But I'll feel her out and see where she is with the drafts. Okay. Anything else, guys, before we get started?
You think you could give us like a quick 5-minute poster presentation, since I'm such a visual dude and I know that you are gonna present very well?
Well, I would have to have a poster. I haven't, to present. Let me see. I don't know. Maybe I can dig up one of my old posters from grad school or something. I don't know if I even have those anymore. I could, but essentially, okay. Let's take a minute or two to look at the template.
I mean, realistically, last class, when we're going back to microbiology, I had an shiitake moment when the first presenters threw their PowerPoint out there, because I didn't have any of that. So it was nice to actually see one and then kind of mold myself.
Yeah, don't worry about it, because it's not going to be a slide deck presentation. It's just going to be your poster. Okay. So the template that I gave you is, let's see if it'll look okay if I open it in here. Oh no, that looks, let me resize it here. Okay, yeah, that's not bad. Let me close some stuff down. So this, let me share this. Here we go. Okay, this is the template. So you'll have a few figures, you'll have your abstract. Okay, if you can't fit your abstract in there, then just put some of your abstract into the poster. And then this is what you'll pull up. Okay, and so you say, hi, I'm John Smith. I'm going to be talking about the Galapagos and marine sea iguanas. Okay. And then give your little introduction. Why is it important? Why did you choose this topic? Maybe, that kind of a thing. And then say, let me divert your attention to figure 1. The circulation of the oceanic currents affect water temperature and nutrient cycling near the Galapagos. And then just talk through your figures. Okay. And that's it. I mean, you got a place for your references down here. And it doesn't need to be in this configuration. You can usually, abstracts are on the left, and it kind of starts with that, and then the references are in the bottom right. I don't care where you put your stuff, but I want you to use this template specifically because it is formatted so that it can be put on the touch screen outside the lab, the biology lab, and on campus. And maybe none of you, I know some of you have been on campus and you know what I'm talking about, and maybe this will never go up there, but I want to have it in that format in case we do want to add these posters, the ones that I deem acceptable. no, you'll all be good, right? But so don't mess with the size of the text. Okay, everything here is arranged so that it will be displayed on that flat screen properly without getting all, its aspect ratio all crunched and stuff. Okay.
Dr. Franz?
Yes.
I thought it was going to be like a actual board, not presented in the computer screen. Is it presented in one, like almost like not a slide, but rather it's going to be presented in the screen rather than a actual board? I'm kind of confused.
Yes. You're going to use that slide, that PowerPoint slide, to make your poster. That way you don't have to print off anything. I don't want you guys to have to worry about that. Now, if you've printed off a poster, if you've made a physical poster, then that's okay. You can present with that. Okay. I don't want you to have to, redo it or anything. But the idea is that you just use that slide and then pull it up on the screen and just talk it through. Okay.
Thank you.
And you want us to actually fill in that particular template that you're showing right now. Gotcha. Okay. And the figures, we can pull those from the papers that we're using, right?
Yes, you don't have to make your own figure. Now, if you want to, that's fine. But, some kind of images are always good. No one wants to just see a bunch of text. So, pull a figure from a paper, pull another figure from a paper, pull a table if you want to, because, even though tables are text, they have a nice way of condensing the information. So, combination of tables and figures, put your abstract in, and then your references, and you're good.
And again, just one singular slide, no other screen.
Just one slide. So it's supposed to simulate a poster presentation. So if you were to go to a science conference and your abstract, you want to submit an abstract because you've got some really cool research and you want to share it, you can apply for a talk or a poster presentation. So usually if you don't get a talk, then you'll make a poster. I mean, an actual big, huge poster, and you roll it up and you take it with you and you travel, and then there's a big, huge room, and there are like a couple hundred posters all put up. And then scientists walk around and they look and they wait and they see a poster that catches their eye, and then they go up and they talk. And it's a way for socially awkward scientists to, discuss their research and potentially collaborate. There's usually wine and beer because that's what socially awkward scientists often need to help, get them a little bit more social. So that's what this is simulating. We won't be drinking beer and wine, at least I won't, but that's what we're kind of doing here. Okay. And so you walk up to someone's post and you're like, oh, and you look at it, you like, so tell me about, tell me what's going on here. And you have it's like your elevator pitch, right? You got 5 or 10 minutes to convince this scientist that what you're doing is cool and worthwhile. Okay.
Thank you.
Any other questions? We ready to jump into it?
Carl, I did have a really quick question about the homework 5 due tomorrow.
Yeah.
It's just a small thing. It's on the for number 17F. There's no value for N2.
Okay.
Yeah, we have initial pressure. I have a pressure for NO of 10 atmospheres, and then it says N2 equal, O2 equal 5 atmospheres. And I just wanted to let you know before that's due tomorrow.
Okay. That comes from 17 in the book. So what I recommend, Rachel, thank you for bringing that up. I recommend that we go to that chapter and we go to problem 17 and we look at F. I see. It says N2 equals O2 equals 5. So that means that both N2 and O2 are 5 atmospheres.
Okay, thank you, thank you. I was just like, wait a minute. Awesome, thank you for clarifying.
Scientists are lazy. So, the less you have to write, the more likely you are to proceed in that direction. Equilibrium for scientists is to predominate toward the lazy end of the reaction. But I totally see how you would think something was missing there. Okay. Shall we? We shall. Let's do it. Okay, so we're going to be talking about acids and bases today. And eventually, we'll get into equilibrium with acids and bases. So again, the nice thing about everything we've learned is that it all just kind of piggybacks on itself. And so now we're going to be thinking about equilibrium in terms of acids and bases and giving off hydrogen ions or receiving hydrogen ions. Okay. And so when we talk about what's going on here, acids, for instance, there are 3 different types or definitions: the Arrhenius acid, the Bronsted-Lowry acid, and the Lewis acid. They all kind of mean the same thing. But for the Arrhenius acid, that means in order for something to be an acid, it needs to increase the concentration of hydrogen ions in an aqueous solution. In order for it to be classified as a Bronsted-Lowry acid, it has to donate a proton. Okay, so the difference between Arrhenius and Bronsted is not much, really. It's just semantics. If you are donating a proton, in this case a hydrogen proton, you are going to increase the concentration of hydrogen ions. And in doing so, you satisfy the Lewis acid definition, being that you donate a proton, and as a result, you accept an electron. Okay? So 3 different ways to think about what acids are doing in solution, what makes them acidic. Now we're going to drop the base. I'm not going to play ice baby today. I don't think we'll get into ice tables yet. But no, we're going to drop the base and talk about the 3 definitions of what a base is. So if a base, or if a Arrhenius acid is something that increases the hydrogen ions, an Arrhenius base is going to be something that increases the hydroxide ions. So if you put an OH and an H together, you get H2O. So we're just looking at the relationship of putting different substances in water. That's what an aqueous solution is going to be for us, okay? So an Arrhenius base increases concentration of hydroxide ions. A Bronsted-Lowry base is going to accept the proton, right? Because a Bronsted-Lowry acid donates a proton. And then a Lewis base is going to donate an electron. So it's just the reciprocal of acids, right? A Lewis acid accepts an electron. A Lewis base donates that electron. And as you can see, it can go back and forth, right? The one thing that's donated is accepted by the other thing, and vice versa, to get some kind of equilibrium or not. Now, there are some things that can be acidic or basic, depending on what happens to that hydrogen ion. And those substances we call amphiprotic or amphoteric. I tend to use amphoteric myself more than amphiprotic, but they're interchangeable definitions. And it just means a substance that can either be an acid or a base. Okay. So for the example of bicarbonate, we can have bicarbonate forming an aqueous solution. So we can write it like a reaction. We have bicarbonate reacting with water to form its conjugate base, which I'll talk about in a minute, and the conjugate acid. Okay, so in this case, we have bicarbonate forming a base, just carbonate. And then we have this H3O. So what gained the hydrogen ion? The water did. The other scenario is that bicarbonate reacts with water to form carbonic acid. And so now that this water is donating the hydrogen to become OH. And so in that case, it was acting like a base. Okay. So what could we do for these other two? What about hydrogen sulfate? How could we write that plus water? Here, let's see if we can, let's do that. Let's write hydrogen sulfate plus water and see what the different options are, okay? I want you to try this on your own, given what I outlined above, and then we'll work on it together, okay? So we write HSO4 plus H2O and that will give us, well, in one case, we'll have H3O, right? In one of those scenarios, we're going to have a hydronium ion. Oh. No. Actually. Let's do it this way. One situation is that we could get H2SO4. In another situation, it gained a hydrogen. What happens if it loses a hydrogen? Then we just have SO4. H2SO4 is sulfuric acid. So in that context, this would be a base. SO4 is now going to be a base. So hydrogen sulfate in that case must be an acid. So then you just have to balance it out. And to do that, I think the water's on this side and the hydronium is on this side. Because that's 4 hydrogens and 4 hydrogens. And then here, if we put hydronium on this side and water here, we get 4, and this must be 2, right? Yeah. No, that wouldn't be right. Because if this is the base, this must be the acid. So then we would write it like this. I think this will make more here. Let me actually stop sharing the screen. I think this would make a little bit more sense if it's not that clear right now. When we get to conjugate acids and conjugate bases. Let's make this big. Okay. So in this case, an acid is donating a proton, becoming a base. So if this is a base and this is an acid, then we have to have a base on this side and an acid on this side. Okay. Same here. This turned into an acid. So that means over here it's a base. And hydronium is an acid, and water, in this case, is a base. Because water is amphoteric. It can be an acid or a base. Now, what about water? The last one, H2O. Well, we would just say H2O plus H2O gives us, what do you guys think this would be? Ah. Four hydrogens, 2 oxygens, 2 oxygens. And then in that case, right, this is the acid, this is the base. And so one of these lost a proton, so it's an acid. One of these gained a proton, so it's a base. So water is amphoteric, hydrogen sulfate's amphoteric, bicarbonate is amphoteric. Okay, where is... Get back to my slide deck here. Sorry, there we go. Okay. Now, with that in mind, whoops. We can say, as I said, that water can be a base and accept a proton from an acid. And if so, it's going to have some kind of conjugate. Okay. If you put hydrogen chloride or hydrochloric acid in water, it's a strong acid. It's going to get rid of that hydrogen. That's going to be an ion, and it's going to go and bind with water and form H3O. Okay. You're going to have a conjugate acid, a conjugate base, and the production of hydronium, H3O. Conjugate just means to come together. Okay. So acid-base reactions always have their respective or conjugate base and acid. So if we look here at this generic formula down here, we have nitrous acid losing a hydrogen to form NO2. So that acid goes and yields its conjugate base. If that is the acid, if nitrous acid reacts with water, then the water, because it's amphoteric, it can be acid or base, it's going to be a base on this side. Okay, and it's going to form its conjugate acid, H3O. In general, when you have a really strong acid, you're going to have a really weak base, conjugate base, right? Or if you have a really strong base, you're going to have a really weak conjugate acid. Water is a weak acid and a weak base. H3O, or hydronium, is a strong acid. Okay. So a weak base is going to drive a strong conjugate acid in this case. So let's try this. Identify the acid and the base and the conjugate acid and base. We already did this first one, so we can do this. We already did both of these actually, really. So let's look here. Okay, let me do my text. I'll write it. So what do you guys think? What do you guys think sulfuric acid is, an acid or a base?
Acid.
Acid, yeah. So that's going to be an acid. And if that's an acid, then H2O in this case must be a base. What is the conjugate base on the other side of the arrow? Hydronium or hydrogen sulfate? Or maybe put it this way. What is hydrogen sulfate? The conjugate what?
Base.
Base, yes. And hydronium is the conjugate acid. Oops, come on. Let me make you wider. Huh. Maybe like this. Whoops. Sorry, guys. I don't. There, select. Maybe that's going to do it. Is that going to let me do it? There we go. All right. Same thing down the bottom, right? So, bicarbonate is going to be a base, right? Bicarbonate is, you put bicarbonate with sodium and you got baking soda. Baking soda is basic. That's why when you add it to vinegar, which is acetic acid, you get a neutralization. You get water and then the release of a bunch of carbon dioxide, which is how you make your volcanoes at home, right? For the science fair or with your kids. So we know that that's a base. And H2CO3 then must be our acid. Okay. So what does this look like? If we were to type this out, we would say that this is our base. If that's our base, then water in this context must be the acid. That's it's the switch of our first problem. And then if that's the case, then H2CO3 or carbonic acid is our conjugate acid, and OH is our conjugate base. And, if it's not absolutely clear to you guys, what's acids and bases, good rule of thumb is that your hydronium, right? If you see hydronium, that's going to be an acid. If you see hydroxide, that's going to be a base. Okay, think sodium hydroxide, right? Sodium hydroxide is a strong base that we use to neutralize acidic solutions. Just like you can use a strong acid, hydrochloric acid, to neutralize a very basic solution. So if you see these, you can then backtrack and infer what must be then the conjugate base or the conjugate acid. Now, what makes something strong or weak? It's not their concentration per se, right? A lot of students, I think, make this connection that, well, if there's a lot of that molecule, it must be what makes it a strong acid, right? Or if it's really dilute, it must be weak. But that's not actually what makes something strong or weak. It's their ability to dissociate in water, meaning their ability to give off that hydrogen ion or that hydrogen proton in water. So if you have a molecule that completely dissociates, meaning every single molecule of that flavor gets rid of its hydrogen, now you have a solution that has a lot of hydrogen ions that will then form conjugate bases. And so that's going to be a strong acid. Strong acids dissolve things. Some do. And so part of that is by giving off these hydrogen ions that then attack other molecules that make up the material that you're wanting to dissolve. By that association, we can say that weak acids, they like to hold on to that hydrogen ion. They're not going to readily give it up. They're just going to give it up a little bit. And so they're going to be not as strong. They're going to be weak. And this is giving you an idea of strong acids, where they are on the spectrum versus weak acids. And it gives you their Ka, which we'll go into later. Okay. So strong acids completely dissociate, or you could say they completely ionize. It's the same thing, interchangeable. Whereas weak acids only partially dissociate or partially ionize. Okay. So if you have in this generic equation here, what this is depicting, HA stands for the acid, okay? The hydrogen bound to the acid, A. Plus water leads to the conjugate base, A minus, right? It's lost its hydrogen. So now it's the base and then H3O or hydronium, the conjugate acid. Now, if equilibrium lies really far to the right or to the product side, what does that mean? That means the acid is strong because it's given up all of its hydrogen. This HA, all of the HAs in solution have dissociated from each other. So now you don't have any more HAs, you have all product. So far right, all product, strong acid. However, if you have a situation where H and A are perfectly happy together and just some of them give up their hydrogen ion, then the reaction is going to predominate, right? In the context of equilibrium, the reaction is going to predominate on the reactant side. And it's going to be then a weak acid. Okay. That's what makes it strong or weak. So here's some different ways of demonstrating that. If we have hydrochloric acid, that is a strong acid. So when you pop HCl into water, it's here, HCl into water, all of the hydrogens are going to pop off of that chlorine and they're going to form hydronium, right? And then you'll have hydronium in a C, or the hydronium C with little islands of chlorine, okay? Completely dissociated, strong. But hydrofluoric acid, in contrast, is weak. So when you put this hydrofluoric acid molecule in with water, you get some dissociation, right? Here and here, which then form hydronium, right? Here and here. But not all of them dissociate. So you end up with, you still have hydrofluoric acid molecules in solution. So it's weak. And we can write that, if we wrote that as a formula, we could write that for hydrochloric acid being a strong acid with just a single arrow, showing that it all goes to product. But with a weak acid, we write it like an equilibrium, okay? Because this fluorine was liberated. But then remember, when that's happening, there's a rate of reaction happening where those hydronium ions that are formed are now losing that hydrogen and giving it back to the fluorine, okay? So it's going back and forth to some degree. It predominates on this side though, on the reactant side. Just as, you know, technically you could have hydronium ions form back into HCl, but then the rate at which they get rid of those hydrogens is higher than the rate that the hydronium ions give the hydrogens back, right? In this case, this rate is less than this rate, so it favors hydrofluoric acid. Okay. All of these are just different ways of explaining the same concept, though. The ability and desire for molecules to dissociate with their hydrogen. Okay. Any questions on that? All right. Hopefully conceptually straightforward. This is just a diagram showing you the strong acids, so perchloric acid, sulfuric acid, all the way down to nitric acid. These are going to completely dissociate or ionize in water. So these are the strongest acids, all right? And then from there, it goes down in their ability to, in their ability to dissociate until you get to water. Water is technically, pure water is neutral, right? And then once we get past water, we have things that do not undergo acid ionization at all, okay? And then we get to bases, okay? Now, what's a base ionization? It's the opposite of an acid ionization. That's now OH, right? Not hydrogen, but hydroxide. And so what that means is that sulfide ions and all the way down to methide ions are going to completely dissociate and lose that hydroxide and just become their ion form. And that's what confers their strength, whether it's a strong base or a strong acid. Okay. Again, if the attraction between the hydrogen and the molecule it's bound to form an acid is weak, meaning it's not a strong reaction, or it's not a strong attraction, then it's going to give off that hydrogen readily, and it's going to favor a forward direction toward the products. And so that's a strong acid. If the attraction is strong, it's not going to give off those hydrogen ions. It's not going to ionize as much to form hydronium. And so it's a weak acid.
Sorry, what does A stand for in those again? Acid.
So when you have H and A together, that could be, that's going to be your acid, meaning H for hydrogen, A for whatever other atom it's bound to, or molecule it's bound to form that acid. So HA, the A could be chlorine for HCl, right? It could be a sulfate for H2SO4. And when you take away that H and you get A minus, that's the conjugate base. Does that make sense?
Yeah, I think so. Okay,
great. So so here's our HA, this is our acid, and it gives this hydrogen to a water molecule to form this H3O. Okay, that's the conjugate acid of this water, which is a base in this case. And now that this acid has given away its hydrogen, it's just A minus, meaning it's now an ion. It's charged. It's negatively because it lost that hydrogen, and it's a base now. Okay. So this is just a generic expression or a generic way to write acids turning into their conjugate bases. Okay, good question. Sometimes I jump through that too quickly. So I appreciate you slowing me down and describing that in more detail. Okay, so when you have an acid-base reaction, equilibrium will always favor the reaction that moves the proton or the hydrogen ion to the stronger base. Okay, let me say that again. Any acid-base reaction will have equilibrium that favors the side, right? We can just talk with the side of the arrow that is moving the proton to the stronger base. Okay. So in this example, we have hydrochloric acid, which is our acid, our HA, plus water, which is our base, forming hydronium, which is our conjugate base, or I mean our conjugate acid, and Cl minus, or our A minus, right? Conjugate base. H2O is a stronger base than chlorine. All right. So the equilibrium is going to be far to the right. So K is much greater than 1. Okay, it's going to favor the reaction that moves the proton to the stronger base. So what that's saying is it's going to favor this side of the reaction. Okay, because this side has the stronger base. And what we know about, if we are moving toward the product side, then K is larger than Q, right? And usually greater than 1. Now let's see what happens when we have the reverse situation. Here, we have acetic acid, that's our acid, plus water, our base, forming hydronium, the conjugate acid, and acetate, the conjugate base. Acetate, the CH3CO2 minus, is a stronger base than water, unlike chlorine, okay? So that means it's going to favor, oh, let me get to the annotation. It's going to favor this side, right? Because this is much stronger than this in terms of its basicity. And so if it's going to favor this side, that means K is going to be less than 1. Okay.
And how do we at this point know which one is a stronger base or acid? Or are we kind of just like memorizing which ones are like
You won't
extreme?
really, that's a great question. I don't really expect you guys to, for instance, memorize this table, right? Hopefully, if you've learned anything this quarter about me, is that in addition to me liking coffee a lot, I don't really put a big emphasis on memorization of these kinds of things, okay? So if you have a problem and you need to know that, then you'll have the opportunity to look that up somehow, okay? And I think really this stuff, we're describing this to give you an idea of how acids and bases behave. But there may not be a whole lot of problems where you have to know that when we get to the problem solving part. These are just characteristics, properties of how they behave. Okay, so I don't expect you to memorize. Now, would it be handy if you knew what some of the stronger acids were and some of the stronger bases? Yes, that would speed up things for you. But for this class, that's not going to be required.
Okay, great.
Okay. What time is it? Let's see what I got here. Okay. Let's do a couple slides and we'll take a break. So amphoteric compounds, remember, acids or bases. If we have amphoteric compounds, such as water that can be both an acid or a base, then we have a situation where it's called autoionization, meaning it's not getting that hydrogen ion from some acid, some other molecular acid, like hydrochloric acid. It's just water, one H2O giving away its hydrogen to form hydroxide, and then another H2O accepting that hydrogen to form hydronium, H3O. So that's where auto, self, right? The water is ionizing itself by one molecule giving up a hydrogen and another molecule accepting it. Okay. What does the equilibrium expression look like for this particular process? Well, we would say that H2O plus H2O yields H3O plus OH. One of the waters, one of the H2Os is an acid. One of the H2Os is a base on that left side, right? Because it's amphoteric. The conjugate acid on the right side is the H3O. The conjugate base is the OH. Okay. Now we bring in K. K is still a part of this whole thing, guys. It's still a constant. We can say that the Kw, or the ion product constant for water, is equal to the concentration of hydronium times the concentration of hydroxide. Okay. So the equilibrium constant, again, is equal to the product of your concentration of hydronium ions and your concentration of hydroxide ions. And if you multiply those together for any solution, and you get a Kw of 1.0 times 10 to the negative 14, that means they're equal. They're at equilibrium, I should say. Okay. Now, in some cases, the concentration of hydronium ions is going to be greater than hydroxide ions, and vice versa. But they should still add up to 1.0 times 10 to the negative 14. Okay. So if you have a neutral substance, it's going to have equal concentrations of H3O and OH. But then if you have a situation where you add an acid and you increase H3O, then you must decrease OH, so that when you, again, multiply them together, you still get that 1.0 times 10 to the negative 14 as an equilibrium constant for water.
And did you say that the two waters on the left there, neither one of those is considered an acid or a base, right? They're both amphoteric.
Well, water is amphoteric. So what we would do is we would just assign one of these as the acid and one of these as the base. Okay. So,
Okay.
you know, you would, oh, okay, let's move this up. So if we were going to label the acids, the Brownstead Lowry acids and bases and conjugate acids and bases, we would just say this, we'll just say this is acid. Okay. Because water can be either or, one of them is going to be acid, one of them is going to be base. And that's it. And then we'd say, here we go. We would say H3O is then the conjugate acid. I always put an M. Conjugate acid and the OH is the conjugate base. Doesn't matter which one you depict. You could switch around those waters, but one of them's acid, one of them's base, always. Okay. So I'll leave this problem up and we'll take a 10-minute break. Let's take an 8-minute break. We'll meet back at 2:10. Look at this if you want to, and see if you can come up with the concentration of H3O and OH of pure water at 25 degrees Celsius, okay? And we'll be back at 2:10 to go over this. All right, folks, 210. Here's the problem. We know that, again, come on. Kw is equal to the concentration of hydronium ions times the concentration of hydroxide ions. And Kw is 1.0 times 10 to the negative 14. So if that's the case, what is the concentration of hydronium and hydroxide ions in pure water? Now, to do this, we make the assumption that in pure water, it's amphoteric, and there'll be equal numbers of hydronium ions and hydroxide ions forming. So in that case, the concentration of hydronium ions is equal to the concentration of hydroxide ions. And so it could just be essentially Kw equals, let's just say H3O squared, right? Because if these values in pure water are equal, and Kw is equal to this times that, if these are the same values, it's one of them squared. And so if we have Kw being 1.0 times 10 to the negative 14 equals hydronium ion concentration squared, then all we have to do is take the square root of both sides to get our hydronium ion concentration. And the square root of 1 times 10 to the negative 14 is just 1 times 10 to the whatever half of that is. 1.0 times 10 to the negative 7. Is equal to our hydronium ion concentration and our hydroxide ion concentration. And remember, that should make sense, right? Because then if we said these were equal, if they're both 1.0 times 10 to the negative 7, and I told you that these have to add up to 1.0 times 10 to the negative 14, well, it does, right? 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7 is 1.0 times 10 to the negative 14.
Do those two concentrations have to be the same though?
In pure water, yes, but now this is just the beginning. Now we're going to say, well, what happens when they're not the same? What happens if the hydronium ions have a concentration higher? Well, then this, by default, must decrease. So good question. The answer is depends. So let me go back to the slide deck and we'll get to something like that. Okay. So this autoionization equilibrium can be applied to all aqueous solutions. Okay, so if it doesn't have to be pure water, right? If we're talking about adding, again, hydrochloric acid to water, we still have the water undergoing autoionization and some equilibrium occurring to give us a constant of Kw equals 1.0 times 10 to the negative 14. As you have an acidic solution that is then adding additional hydronium ions, now you don't have that pure water where hydronium and hydroxide ions are equal. Now you have a solution where you have more hydronium ions because you've added an acid to it that gives away that hydrogen and then is accepted by the water to form H3O. Now, what that means, if the constant is still the same, that means that the hydroxide ion concentration must decrease, so that when you multiply those two together, you still get 1.0 times 10 to the negative 14. So let's try that, okay? We have a solution of carbon dioxide in water and an hydronium ion concentration of 2.0 times 10 to the negative 6. What is the concentration of the hydroxide ion at 25 degrees? Now, what is carbon dioxide in water? That's just fizzy water, or as my kids say, spicy water, right? It tends to be a little bit acidic, very, very mildly acidic. And you'll understand that by looking at 2.0 times 10 to the negative 6. That'll make sense later on. But how would we go about calculating that? How would we set that up? Here's my, right there it is. Well, we know that the KW is always going to be 1.0 times 10 to the negative 14, and that's equal to the hydronium ion concentration, which in this case is 2.0 times 10 to the negative 6 times hydroxide ion concentration. So we just divide both sides by 10.0 times 10 to, or I'm sorry, 2.0 times 10 to the negative 6. And that will give us our hydroxide ion concentration. What is that? What is, stop sharing. What is 1.0 times 10 to the negative 14 divided by 2.0 times 10 to the negative 6? Anybody?
Five times 10 to the negative 21.
5 times 10 to the negative 21. Anybody else get anything different? No? Okay. Well, if you multiply this by 2.0 times 10 to the 6, then we should get 1.0 times 10 to the negative 14. So let's try that. Negative 6.
Did you want to multiply the left side by 2.0 times 10 to the negative 6? Or, oh, no, sorry, I just read that wrong. Never mind.
I'm not, so something's not, did I write that down correctly?
I said it wrong. It's 5 times 10 to the negative 9, not negative 21.
That sounds better. Thank you. that looks to be more in the ballpark, right? Because 6 and 9. Okay. So then, again, to check it, you could just multiply 5.0 times 10 to the negative 9 by 2.0 times 10 to the negative 6, and that should give you 1.0 times 10 to the negative 14. Okay. So baby steps, baby steps.
Isn't it 2.0 times? Oh no, never mind. Sorry, I keep on just reading the wrong thing. I'm confusing myself.
No worries. We get through this together. All right. So that's that. So to summarize, a neutral solution, or like pure water, is going to have equal concentrations of hydronium and hydroxide. And if they're equal, that concentration must be 1.0 times 10 to the negative 7, so that when you multiply them together, you get 1.0 times 10 to the negative 14. Now, if you have an acidic solution, that's going to increase the hydronium ion concentration, right? For instance, like, let's go back to this, right? Is 2.0 times 10 to the negative 6 more or less than 5.0 times 10 to the negative 9? It's a bigger number, right? So again, when we add an acid, in this case, the carbon dioxide, to water, made it acidic because it actually forms carbonic acid. But that's extra detail that you don't need to really know. But what that's doing is it's increasing the hydronium ion concentration so that it's greater than the hydroxide ion concentration, and therefore it's acidic. Basic solution is going to increase the hydroxide ion concentration, and therefore the hydronium ion concentration is going to fall. And in all aqueous solutions, regardless of the concentration of hydronium and hydroxide, they have to, when multiplied together, equal 1.0 times 10 to the negative 14. So let's try some more things here, okay? Calculate the hydroxide ion concentration at 25C for each of these solutions, and then determine if it's acidic, basic, or neutral. How do you know if it's acidic? Well, if the hydronium ion concentration is higher than what you calculate for the hydroxide ion concentration. If the hydronium ion concentration is greater, or I'm sorry, is less than the hydroxide ion concentration that you calculate, it's basic. And if they're equal, it's neutral. So work on these. I'll give you guys a few minutes and then we'll go over it together, okay? Who goes there? What's up, man?
It's snowing outside.
Oh yeah. Maybe a little bit.
When you're done working, can we play a little game?
I gotta go. Remember?
Oh yeah, when you're done working.
Go play. Okay. Still working. Okay. Thanks, buddy. All right, guys. What do you think? Anybody get to the first one? How do we set this up? Well, we know that the equilibrium, hopefully you guys can see my writing. It looks a little bit pale. 1.0 times 10 to the negative 14, or kW, is equal to, they give us the hydronium ion concentration, 7.5 times 10 to the negative 5 times whatever. This is what we're trying to solve for. So to get this, we divide both sides. Or I'm sorry, yeah, we divide both sides by 7.5 times 10 to the negative 5. What happens when you do that?
I get 1.3 times 10 to the negative 10.
Okay. Is that less than, equal to, or greater than 7.5 times 10 to the negative 5?
Less.
Yeah, it's a smaller number. So that means the concentration of the hydroxide ions is less than the concentration of the hydronium ions, and therefore it is acidic. 1.0 times 10 to the negative 14 divided by 1.5 times 10 to the negative 9. What's that?
.7 times 10 to the negative 6.
Okay, 6.7 times 10 to the negative 6 is a bigger number than 1.5 times 10 to the negative 9. So therefore, the concentration of hydroxide ions is greater than hydronium. And so this B would be basic. Now, do we even need to do C?
No.
No, because they say that the concentration is 1.0 times 10 to the negative 7. Well, we already did that problem. We already know that that is essentially the square root of the kW. So this one must also be 1.0 times 10 to the negative 7. And therefore, this C solution is neutral. That's all there is to it, guys, at this point. Okay. Let me get back to my slide deck. And we'll have some more fun. Okay, so this brings us to pH. You've all heard of pH, right? pH is how you test whether or not something is acidic, basic, or neutral. pH is really just the negative base 10 logarithm of the concentration of hydronium ions. Okay. All that is we're taking the constant. So as we've talked about, you add an acid to some water, it's going to change the concentration of hydronium ions to something. If you take the negative log of that concentration, you get pH. That's it. P is just an operator. Some people say to the power, right? So the power of hydronium. So pH is simply just the negative log of the hydronium ion concentration of a solution. Right? So the H in pH is analogous to the hydronium ion concentration on the other side of this equation. You can replace it with X, whatever. Okay. Now, everything we've been dealing with, these concentrations are small numbers, right? equilibrium, the ion product constant is 1.0 times 10 to the negative 14. That's small. If we take the negative log of that, it flips it, and it makes it a whole number. Okay, and that's why we do this. Because give me a pH. What's an example of a pH of something? If I were to take the pH of something, what?
7.8.
What's that?
7.8.
Yeah, 7.8. Right, that's physiologic pH. Potentially. 7.4, right? 7, not 1.0 times 10 to the negative 7. 7 is neutral, right? That's why we do this. It makes it easier to compute things by taking the pH or just taking the negative log of these concentrations. Pretty cool, huh? So if we know that the ion concentration of hydronium and the ion concentration of hydroxide multiplied together gives us 1.0 times 10 to the negative 14. And we know that pH is the negative log of the hydronium ion concentration. If you want to plug it in, take 1.0 times 10 to the negative 14 and take a negative log of that. Or just take a log of it and then flip the sign in your head. What do you get? The log is just the base of 10. So if it's 14, it's 10 to the negative 14. The negative log should be 14. 14 because it's a negative, so you're reversing that 1.0 times 10 to the negative 14. And you're getting rid of that 10, okay? And so if we want to now look at things in the terms of pH, we can say that the negative log of the hydronium ion concentration plus, not times, plus the negative log of the hydroxide ion concentration is equal to the negative log of the ion product constant, which is equal to 14. So what that means is that the pH plus the OH equals 14 pKa, or well, in this case, pKw. We'll get to pKa later. All right. pH is the negative log of hydronium ions. pOH is the negative log of hydroxide ions. And if you add those together, you get 14. And if you guys know about the pH scale, it goes from 1 to 14. 1 being very acidic, 14 being very basic, 7 being neutral. This really is a beautiful thing, I think. I really love pH. I think it's just a very elegant way of looking at this concept. So I hope you guys like it too. We'll see. We'll see what you guys think. Calculate the pH of a solution at 25C. And again, these are all at 25C because things change when you add heat or take away heat, right? In terms of solutions forming. So right now it's at 25C, and then indicate whether it's acidic or basic. For A, the hydronium ion concentration is 1.8 times 10 to the negative 4. For B, they give you the hydroxide concentration. See what you guys can come up with. Remember, negative log of the hydronium ion concentration plus the negative log of the hydroxide ion concentration equals 14. switch to black. What'd you guys get for the first one? Anybody? How do we set this up? Well, pH, remember, is equal to the negative log of the hydronium ion concentration. What was that hydronium ion concentration they gave us for A? 1.8 times 10 to the negative 4. So if you type that into your calculator, 1.8 times 10 to the negative 4, and we do the log of that, I get a negative 3.74. But it's a negative log, so it's positive 3.74. Is that acidic or basic? It's below 7. 7's neutral.
Basic.
Close. The opposite of basic.
The opposite.
It's acidic, right? Because remember, on the scale of 1 to 14, 1 is very acidic, 7 is neutral, and 14 is basic. So 3.74 is in between 1 and 7, so that's going to be acidic. Okay.
Why is it sometimes called acidic and alkaline?
Well, alkaline is just another word for basic.
So it means the same thing. It's not like the words are used in different contexts.
No, if something is alkaline, that just means it's basic. So if you look for the alkalinity of someone's blood, you're looking at how basic their blood is. Okay. Alkaline batteries use a base. Because what do batteries have in it? They have battery acid. So it's a way to exchange the flow of hydrogen ions, which we'll get into that in Chem 103 when we talk about battery chemistry. But for now, what do we do for B? We've got to do something first. We can't just do the pH of this number because pH is of hydronium ion concentration. But if we have the hydroxide ion concentration, how can we find the hydronium ion concentration? Mhm.
KW divided by
Yes.
concentration.
Yes. So we know that this times the hydronium ion concentration is equal to 1.0 times 10 to the negative 14. So 1.0 times 10 to the negative 14 divided by 1.3 times 10 to the negative 2 should give us a concentration of hydronium ions. And what happens when we do that? What do we get?
7.7 times 10 to the negative 13.
10.7 times, sorry, what was that?
7.7.
Oh, sorry. 7.7 times 10 to the
Negative 13.
negative 13. Okay. So now that we have that number, what does that mean?
We can find the pH now.
Yes. So how would we do that?
Take the negative log of that number.
Okay. You got it. What's the negative log of that?
12.1.
Okay. Now, what's the opposite of acid? Basic, right? It's going to be right here. Or alkaline. 12.1. It's going to be a base. There's going to be basic. Okay. Any questions on that? Okay. Man, time is flying by. We've got 8 minutes left. I haven't gotten nearly as far as I was hoping, but that seems to be the general trend. Unfortunately, this means we got to cover a lot when we get to Chem 103, but it's all good. It's all good. I'd rather go slow and have you guys understand it than rush through and you know, not understand it, right? Because what's the point then? So as we said, in pure water, the concentration of hydronium and hydroxide ions is 1.0 times 10 to the negative 7. If you take the negative log of that, you get 7. That's neutral. In acid, it has a higher concentration of hydronium ions. If you take the log of that, it's going to give you something less than 7. Base is going to give you something that is greater than 7. So acidic solutions are going to be less than 7 pH, neutral 7, and basic greater than 7. And here's some examples. And again, you don't have to memorize any of this, but it just gives you an idea of how pH is related to concentration of ions. So if we have 10 to the negative 1, that's going to give us a pH of 1. 10 to the negative 4, pH of 4, right? And so on and so forth. And this gives you some examples of pH and common things. So our digestive juices, right? Where that falls in the spectrum, very acidic, right? Wine, acidic. Coffee, acidic. Rainwater is acidic. Even if it's not acid rain, as we always, when I was a kid, I thought acid rain would be a much bigger deal than it is. It's kind of like quicksand. Have you guys seen the meme? Like, when I was a kid, I thought quicksand would be a much bigger deal in life. I've never been stuck in quicksand. I've never been burned from rain. So luckily those things are rarities, but Once we get to past pure water, then we get to things like our blood. Slightly basic. Ocean water, baking soda, milk of magnesia, right? Milk of magnesia is what you take when you have indigestion because it neutralizes the gastric juices that are working their way up through your pyloric sphincter. Okay. Bleach, sodium hydroxide, very basic, right? And you don't have to memorize that. That's just for your own information. The 7 strong acids, meaning the ones that really completely dissociate, are these here, okay? Again, you don't have to memorize these strong acids, but if you do know, for instance, that perchloric acid is a strong acid, it's going to help you do your problem solving later on. You can take certain assumptions. What are those assumptions? Well, if it's a strong acid, that means it's going to completely dissociate. And so that the concentration of hydronium ions is going to be equal to the concentration of that acid, the molarity of that acid for strong acids. Now, when we talk about weak acids, they don't completely dissociate. So you cannot make that exact translation from concentration of the acid itself, the molarity, to the concentration of the hydronium ions. But for strong acids, for these 7 strong acids, we can. Okay. So if we have 0.1 molar solution of hydrochloric acid, what is the pH of a point, or what is the pH and what is the pOH? That's what it's asking for. Do we have time to do this? Okay, let's do it and then we'll be done. Okay. Hydrochloric acid is one of the 7 strong acids. So we can say that the concentration of the hydronium ions is equal to the concentration of the acid itself. So if the concentration of the acid is 0.1, then what's the concentration of the hydronium ion? Anybody?
0.1.
Bingo, yes, 0.1. So how do we find pH? We take the negative log of that. What's the negative log? Of 0.1. What do you guys get?
1.
1. That makes sense. Because hydrochloric acid is a strong acid. Yeah, great, right? Because the pOH and the